Welcome everyone to our last video on Chapter 2, Lesson 6. This is kind of a review lesson. Now that we know how to graph rational functions, our goal is to be able to describe them using all the language that we learned at the very beginning of this semester. So just a quick recap. If we were to look at this particular function here, we could factor it. And from either of these two versions right here, we'll be able to figure out what the x-intercept is, what the y-intercept is, what end behavior is, and then also vertical asymptotes. Okay, so all of that info has been put up here. We may have needed to graph or think about a few extra points just to figure out what's going on in this chunk and in this chunk, but based on previous assignments, you should feel very comfortable doing all of these things and then getting the graph. So this lesson is focused a little bit more on if you had the graph in front of you, how would you describe it? So we're mainly thinking about this in terms of rational functions, but just remember we can do all of this, all of these descriptions with any other function that we've been looking at. It could be trig stuff from earlier in the year. It could be power functions or polynomials from earlier even in this unit. These are all things that we want to be able to describe if we have the graph in front of us. So we're going to be referring back to this graph quite a bit. So starting here, this is probably going to be one of the tougher things here. What's the behavior near our vertical asymptotes? So you certainly could try some numbers close by. We kind of have a pretty good idea of what the graph looks like already. So we have two vertical asymptotes, so I need to talk about what's going on at -2. Okay, so on the left side of your screen here, we could say that the limit as x approaches, let's see, that's at -2. We could say from the negative side, and this function is, we really don't have a name for it, it looks like, so let's just call it f of x. Okay, so from the left side, what's happening as we get close to -2 on the left side? Well, it's going down, so that's going to be a negative infinity. Okay, but if we were to do it on the other side, so as x approaches -2, but now with a plus symbol there, that's from the positive side, it's doing the opposite, it's going up to infinity. Okay, we do the same thing at +3, so I'll do that in a different color. Okay, so the limit as we approach 3, we'll start from the negative side. We always have to name the function that we're looking at. So from the left side, this is going down again, so it's going to be negative infinity. We'll scooch that up just a little bit. Okay, and then on the opposite side, what's the limit as we approach +3, but now from the positive side, again, we name the function. Now it's going up on that side, so we're going to be approaching infinity. All right, so that was kind of a tough one. That was a long section there, but now we can move on to some things that hopefully will go a little bit faster. Okay, so if we look at the domain, what x values work? Well, really, we want to look at what x values don't work, and we've kind of touched on them already. It's -2 and +3. So we would say that for the domain, okay, there's lots of ways you can do this. If we're going to do interval notation, we're starting at -infinity. We're going all the way to -2, but we're not going to include it. Oops, I already messed up there. Let's undo that. We have a little u. Okay, we're going from -2 then to the next chunk, which ends at 3, another u, and then we're going to infinity. You could also say something like all reals except x equals -2 and +3. So lots of options for that. Okay, next question is what's the range? Okay, and I know there's some issues maybe thinking through this, and I know that particularly there's a gap at y equals 0 here at the very ends, but this little chunk here, it's covering every y value. Okay, so the range is going to be every possible number. So you could do something like this, you could do something like this, something that conveys all numbers is what we're looking for there. Okay, so we'll kind of cut that off there. Okay, continuity. Again, we could rephrase the question. We could say, where is it discontinuous? It's discontinuous at -2 and at 3. X equals -2, x equals 3. This is kind of asking for where is it continuous? And so if we look at this, if we go back to the graph, it's really continuous wherever it is, wherever we can evaluate it. So the answer in the end is going to be the same thing as the domain. So I think I'm just going to write that for my answer here. is just same as the domain. And I think it's fairly safe to say that for most of these kind of questions, that's going to be how we could answer it. Just the same sort of notation that we use for the domain. All right, increasing, decreasing, or constant. Okay, where's it going, uphill or downhill? Well, if we look at this, it is basically always going downhill. There's some changes at those vertical asymptotes, but it's always going downhill. So we would say it is decreasing, but we do want to kind of explain where. So we're going from negative infinity to negative 2, and then from negative 2 to 3, and then from negative 3, oops, sorry, that would be a positive 3. Let me see if I can undo that. Close enough. All the way to infinity. So again, this looks a lot like the domain. I want to write it out here though because it will not always be that way. There might be cases where part of the time it's decreasing, but part of the time it's increasing. So I don't just want to assume that it's going to be the same as domain. A lot of times though with continuity, it is. Okay, is it even, odd, or neither? And this is one where we technically could prove it based on this equation, but if we look at the picture, since we have the picture in front of us, there really isn't any symmetry here. I can't reflect it across the y-axis. It would not look exactly the same. This little piece right here especially would give us some issues, but so would this end reflected over here, this end reflected over to that side. It's not rotational either because this little piece right here would end up over there. It's not going to look exactly the same. So for this one, we kind of have to say it's a neither. Okay, and then what's our next topic here? Is it bounded? Does it ever go above? Or does it never go above or below a certain number? And you could say over here it's kind of bounded, over here it's kind of bounded, but we're looking overall, and because of this middle piece right here, it's going to hit every single y value in the middle here. So just like we looked at this for range, we're going to kind of look at that little chunk for is it bounded, and in this case, it's not. It's an unbounded function. All right, and our last idea is are there any extrema, are there any hills or valleys? Well, over on this side, as we go to the left, it's going to keep slowly growing, never going to go above 0, but it's also never going to start to dip again, so there's no hill over there, no valley over here for kind of the same reason. And going through this little piece right there, obviously it's always decreasing, so it starts off really high, gets really low. There's no extrema there either. So again, that's not always going to be the case, but if you can see a hill or a valley, an overall max or an overall min, then you would write that down. So we would say for this little chunk here that there were none. Okay, so hopefully that was a good little quick review of what do we mean by some of this terminology. Certainly this is not like the example that will fit every sort of thing that you're going to see, but hopefully it gives you a quick little review of what some of this language means.